So 3 years ago, with the naming of 4 new elements, Moscovium, Tennessine, Oganesson, and Nihonium, we completed the existing chart, Mendeleev chart. And right now we are facing the question, are there more elements possible? What can we do more? Can we see any more elements and place them in this chart? So some atomic theorists can say we can reach up to element 172. Element 172, we can put up to 172 electrons in the atom. There are good reasons to say that there's maybe only 137. So the fundamental point is that we need a stable nucleus to have an atom. So there has to be a source of Coulomb force for the atom to exist, and the nuclear stability is essential for the existence of the new elements. So there is a apparent order placed from this self-organizing of electrons in the atomic shells when we put more and more electrons in the field of the nucleus, and the order emerges from this. Now, nuclei are more complicated. They consist of protons and neutrons. We can again put a nuclear equivalent of the Mendeleev chart. So you see protons and neutrons ordered into this particular representation. Now, at the end of the nuclear chart, it's very difficult to make very, very heavy nuclei. Coulomb forces would like to explode the nucleus, deform, disintegrate it, and it's very difficult for these objects to exist. In particular, it is difficult to see how the heavy nuclei existed. So for many years, we have this concept of the island of stability, where shell effects, similar effects to those in an atom, will stabilize this nuclear drop, and they will lead to formation of stable system also for these very heavy elements. So the specific combinations of protons and neutrons are responsible for this effect. So here we see that if we put 184 neutrons and 126 protons, we will reach a stable system, stable super heavy elements. So how do we make those heavy elements? We have to fuse 2 stable isotopes in nuclear reaction. The problem with those reactions is most of the time we create a system which will disintegrate immediately after it fuses. So the survival of the fused system is a problem. So this is an accelerator in which the 48 calcium atoms were accelerated to be fused with the berkelium nuclei to create new super heavy elements. This will be now soon replaced by the newer machines. And as this research was going for decades, we reached a point where with the discovery of 112 element 112 copernicium, which looked like we reached the limit of our capabilities. And it was very difficult to imagine how to move forward. And with the new method of fusing 48 calcium beams with unstable targets, californium-249, we were able to see the path to the new elements. And this research was championed by Yuri Oganesson. And this so-called hot fusion, where higher energy beams were used for creation of super heavy elements, provided us with the new perspective and completely new way of studying and accessing new isotopes and new elements, including Tennessine. So how do we go about doing Tennessine? We need to collide calcium-48 with berkelium to create this element. The main problem is that the berkelium is an unstable isotope, which has to be also created in the nuclear reactor through successive captures of neutrons. So this is the picture of high flux isotope reactor where there's those berkelium atoms targets can be made, and we put them into the radioactive isotopes were painted on the targets. Now, after this fusion collision with the, between berkelium and argon, you can measure we measured several atoms of Tennessine. The 9 atoms have been measured in several weeks of bombardment of berkelium. So that gives us evidence, and this is the summary of all the results, where we see the increased lifetimes for all the elements as we approach the neutron number 184, which means that we see the evidence for this island of super heavy elements, but we haven't reached it yet. So in order to make new elements, we have to try out new beams. We have to fuse the radioactive targets with the beams of titanium and vanadium to reach element 119 and 120. This hasn't been successful yet, but a lot of effort in new facilities are being placed to do that. Now, the other aspect of this, the nuclear theories predicts a lot more isotopes which we can see. For Oganesson, the element 118, we can expect 100 elements, 100 isotopes to exist, but we don't know yet how to reach it. The other question is, can universe ever make this island of stability, nuclei belonging to this island of stability? So that could be done in some kind of collision of neutron stars, which would generate enough neutrons to provide us with the successive neutron capture and reach these new elements. Thank you very much.